have a network with connections among the nodes. Well, let me have one more like this. Okay, so the idea is to use this connectivity information to gather some intelligence about the importance of the single nodes. And to measure the importance of the nodes, we build the adjacency matrix whose elements Eij are equal to 0 or to 1, depending whether a link exists from node I to node j. And the idea is that we assume that every node has an importance information which we call prestige of node I, and every node is able to take his own prestige and to convey it to its neighbors. So we identified a step-dependent process where we have an initial, so with superscript 0 prestige value for all nodes, and then we end up by determining the prestige for node I at time t plus 1 by considering all nodes j and assuming that every node j gives his own prestige to node I. Actually not all the prestige because it is equally shared between all its outgoing links. So node j provides his prestige to node I if and only if there is a link from j to I, so this is 1, and the prestige is divided by the number of outgoing links from node j. So okay, we call this the out degree of node j, number of outgoing links. And of course, the prestige that is used is the one that was determined in the previous iteration of the method. Okay, this is one possible way to explain what's happening. But what we want to get is actually a stable prestige distribution that does not change in time. So we are asking that this iterative expression has a limit so that for t large enough we have actually a stationary situation, a stable situation where the redistribution of prestige according to this equation does not change the distribution itself. We can see this as a set of linear equations. Okay, everything is linear here. These are the unknowns that we want to determine. But actually, in order to go further and be able to say something about this method, I would like to change the point of view. And what I would like to convince you now is that these values, Ti, can be actually seen as probabilities. Okay, suppose that a user is browsing the web. This is the web. Okay, we have this user model. The user starts from this node. Let's give names to nodes. So the user starts from node 1, and then he proceeds by randomly selecting one outgoing link and clicking on that link. So that if at the initial time the user is at node 1, at the second step he will be either at node 2 or at node 4, both with probability 1/2. Okay, so we can define Pi as, Pit as the probability for the user of being at node I at time t. This means, for example, that with the assumption that I said that initially the user is at node 1, then at the initial time, let's call it t equal to 0, the user will be certainly at node 1 and with probability 0 at the other nodes. So if we interpret the P as probabilities, of course we need some restrictions on the values of P. The probability needs to be for sure less than or equal to 1, okay, between 0 and 1. Otherwise it has no meaning in probability. And the second restriction on the values of P is that their sum has to be 1. Because of course the user has to be at 1 and precisely 1 node at every time. So the sum of all Pi's at time t must be equal to 1. Note that this second constraint automatically implies that all Pi's are less than or equal to 1, given that they are positive. So we usually write the conditions like this. Okay. These two conditions imply that every Pi is smaller than 1, is no larger than 1. And of course we also can define the vector of probabilities at time t as the vector of P1 time t up to Pn at time t. Okay, in this particular case, of course, n is 5. If we have this probability distribution, how do we manage to have the next probability distribution? So, if we know that the user is with some probability at node 1 and so on, how do we deduce the probabilities at the next time step? Suppose the user is at node j at time t. What is the probability of the user being at node I in the next step? Okay, first, the probability is 0 if there is no direct link between j and I. If there is a link between j and I, it depends on how many outgoing links, because remember, the user has an equal probability of choosing one of the outgoing links. So, if we know that user is at node j, then the probability of being at node I is precisely zero if there is no link between j and I. Otherwise, it is 1 divided by the number of outgoing links. So this would be the probability if we knew that the user is at node j. Otherwise, all we have to do is to take all probabilities for all nodes j and weigh them for all nodes j. Okay. So the probability for the user of being at node I is for each node the probability of being previously at node j multiplied by the probability of transitioning from node j to node I. We can also write at every link the probability that the user has to follow that particular link. What is the probability of, if the user is at node 1, what is the probability of following this link? It's 1/2, because there are two possible links to follow. So we can write 1/2 at each of these links. There are two outgoing links from node 2, so 1/2. There is only one node coming out of node 3. So if the user is at node 3, he will for sure follow this link and go to node 4. From node 4, there is only one outgoing link, and again from node 5. Here we have a system given that has 5 possible states, and the transition from one state to the next is given by a probability that only depends on the state the system is in. Let me simplify this. As we said last time, I can give a name to this. For example, I can call it Aij, so that this becomes Aij Pj and T. And Aij is the transition probability from state, sorry, this is a J, from state J to state I. Let's do a couple of steps of this dynamic system. We're saying that at time 0, the probability distribution of the user's position is 1, 0, 0, 0, 0. Okay, the user is with probability 1 at node 1. How does probability propagate at time 1? We can use this equation, of course, or we can simply look at this graph and build the new distribution vector based on the previous one. So, for example, we know that the probability at node 1 is divided into 2 and goes to node 2 and to node 4. So, this one becomes 1/2 at node 2 and another 1/2 at node 4. All other probabilities were 0, so independently on how they propagate, they remain 0, and at time 1 we have this probability distribution. In fact, we know that after one step the user for sure is not at node 1, because he was in the previous step and he was forced away by one of the links. Now, let's see what happens at the next time step. The 1/2 probability of node 2 is equally divided between node 3, so this 1/2 becomes a 1/4 at node 3 and a 1/4 at node 4. Then we have a 1/2 probability at node 4 that propagates without being split to node 5. And the other probabilities, so the probabilities at node 1 and 2 are 0. So this is the probability distribution at time 2. you see that with this process, we get probabilities to be spread among all nodes. In fact, usually, if you let enough time pass, given some conditions of the network, you would expect the user to be able to be at any page. Let's see another pair of steps. So at time 3, we have the probability at node 5 goes to node 1. The probability at node 3 goes to node 4. The probability at node 4 goes to node 5. And nothing else. Here finally the probability at node 1 is shared between nodes 2 and 4. Four goes to 5, and 5 goes to 1. In the next step, finally, every node will have a non-zero probability of being visited. So here, node 5 goes to node 1. Node 1 is split between node 2 and node 4. Node 2 is split between node 3 and node 4. Node 4 goes to node 5. Okay, so you see that at time 5 we have two ways of reaching node 4. 1/8 plus 1/8 is 1/4. Okay, and so on. You see that here at step 5, the user has may be at any node, not with equal probability, but he might be at every node. What I'm asking now is, will this system converge to a precise distribution of probabilities, or will probabilities tend to change in a cyclic way? So I want to reach a stable state. But what will this stable state be? Well, we can find it analytically. In fact, let's write the equations that, explicitly the equations that determine one vector given the previous one. So, the probability of being at node 1 at time t plus 1, well, we just look at the drawing and we see that in order to be at node 1 at time t plus 1, the user had to be at node 5 at time t. That's the only way. So the probability of being at node 1 at time t plus 1 is equal to the probability of having been at node 5 at time t. It's simple like that. What's the probability of being at node 2 at time t plus 1? In order to be here, the user had to be at node 1 at time t, and in that case, it only had a 1/2 probability of going here. So this probability is 1/2 the probability of being at node 1 at time t. Okay? Next, node 3, for exactly the same reason, is 1/2 the probability of being at node 2 at time t. The probability of being at node 4 at time t plus 1 is just a little bit more complex because it is actually the sum of 3 different probabilities. In fact, the user could have been at node 1, and it had 1/2 probability of moving to node 4, or it could have been at node 2 with a 1/2 probability of moving to node 4, or it could have been at node 3, and in that case it would certainly move to node 4. Finally, the probability of being at node 5 at time t plus 1 is exactly the probability of having been at node 4 at time t. Now I'm asking what happens when t goes to infinity. It means, am I going to, can I hope to reach a stable state? The first question is there a stable state? In order to see it, I just move t to infinity, and as we have seen last time, this amounts to removing the t superscript and see if there is still a solution to this system of equations. If I remove t, in fact I want that the state at time t is equal to the state at time t plus 1, so I remove the indices, the superscripts. This becomes a system of 5 equations and 5 unknowns. I just have to solve this to find. And solving this is rather easy because you see P1, P5, and P4 are equal. So I can write, let me put it here. So P1, P4, and P5 are equal because these 2 equations. So we don't need to use them anymore. And every time I find P4 or P5, I can replace P1. So here I can replace P1 and nowhere else. Next, okay, P2 is 1/2 P1, or you see I like full numbers. So P1 is twice P2. So we can replace, every time we find a P1, we can replace twice P2. Here and here. Next, well, let's do the same here. P2 is twice P3. So P1 is 4 times P3. What I really need is the condition that these are probabilities. So their sum P1 plus P2 plus P3 plus P4 plus P5 equals 1, and they are all positive. Okay, I have to add them, these 2 conditions, to the system. So actually, the condition I found here is enough. I just need to find, so let's just replace P3 to all other values here. So instead of P1, we can write 4P3. Instead of P2, we can write 2P3. Instead of P3, okay, we write P3. P4 is another 4P3, and P5 is another 4P3. And all of this is equal to 1. So I get 15 times P3 is equal to 1, and finally P3 is equal to 115. Given this value for P3, I get that P1, P4, and P5 are equal to 4/15, P2 is equal to 2/15, and P3 is equal to 1/15. Or, of course, in as a vector, this is the final probability distribution, the stationary probability distribution. So I know that if at some step, at some time, I have this probability distribution for the user being at each node, at every subsequent step, the probability will remain this one. Which is what I want, because this gives me a measure of importance of all nodes. In fact, if you look at the graph, okay, you immediately get the idea that node 4 is particularly important, because many other nodes point to it. So it's reasonable for node 4 to be important. But now we have a chain of 1 transitions that spread exactly the same importance to nodes 5 and 1. So it's reasonable that the system gives to nodes 5 and 1 exactly the same importance as node 4. And also we get the idea that the node 3 is not that important. In fact, the node can skip visiting it every time by taking the shortcut from node 2 and 4 rather than passing through node 3. Okay, so node 3 is not that important. Can we hope that by repeating these iterations, we end up to this particular distribution? Actually, we already have a hint here of the importance of the nodes. You see that nodes 1, 4, and 5 are more important at this point than nodes 2 and 3. Of course, these are not the final values. So I expect that if we go further, we'll see other modifications to this. In particular, we'll end up seeing that, you see, these 3 nodes, 1, 4, and 5, are twice as important as nodes 2 and 3. But actually, this is not the case, and sooner or later, we will see also differences between nodes 2 and 3. In this case, we can expect that the system converges to a good situation.